So, what questions do you have related to what we have discussed at the seminar or what you have seen at the course? Can you hear me, Prab?
Yes, we can hear you.
Okay, that's perfect. Tell me, do you have questions? Okay, if not, I suggest you to start talking about what on the theories and maybe what we would talk about singular points of a function, about residue of a function in a point. I mean, the things that we have discussed in the course, but you haven't seen yet at the seminar, if you like. We'll use a lot the notion of residue of a function in a point. This notion will be used to compute complex integrals, also real integrals, computed using the residue theorem. Also, you will need them in order to compute Laplace transform and Fourier transform for function. So it will be helpful to know to compute a residue of a point of a function in a point. But first of all, let's remind the Cauchy's theorems. I will share my screen so you will be able to see the whiteboard. Okay. Just a second. I'm sorry. So let's talk about the Cauchy. Yeah. Uh, First of all, I would like to see the attendance list. Just a second. Let's take a look at the attendance. Good. But are you here?
You are interrupting a bit. We cannot really hear you.
Oh, my connection is better than the last, but I see that it is not enough. I will try to speak such that you could understand better what I'm saying. I'm trying to pronounce the words not so fast. And if you have any problems with the connection, tell me, and we'll try to manage to solve it. I will try to explain to you again, maybe that I can understand. Okay, so Alberto here, here. Okay, I would like you to write in chat if you cannot hear. Do you now is one able to hear me?
We've
Because
heard
I
the
don't.
last part, but it is sometimes dropping.
Okay, I'm trying to see the attendance list. But this is the rule. I have to check the attendance list at the beginning, at the end of our session meeting. So, okay, you don't hear me. Just a second. Just a second. Okay. Do you hear me now?
Yes.
Okay. Um, Anna, are you here? Can you hear me? Anna Comega.
Yes, I'm here.
Okay, that's perfect. Audrey,
Present. I'm here.
Pulpo. Okay.
Puteți repeta o dată?
Are you here, Tudor?
Yes, I'm here.
That's great. Pico,
Sunt aici.
perfect. Jacques,
Da.
hello. Nica,
Da.
Bădică,
Da.
Virciurescu,
Da, prezentă.
Adălărit.
Gabriel nu este deocamdată.
Okay. And George.
Present.
Oh, that's perfect. So, let's go on with our session. As I told you, I want you to Cauchy fundamental theorem and Cauchy integral theorem. We'll make a very short recap of the seminar, and after that, if you have questions, you could put me those questions, and if not, I will explain to you more about that you have seen at the course, at the last course. So, what this fundamental theorem tells you? So let's say that you have to compute an integral which is given by I, which is a complex integral, computing on a domain which is given by the condition modulus zero equals to from a constant f of z. So compute this integral, but first I have to take a look at the function and at the domain. This domain means what? What is this domain? What is this? This is circle. Okay. So this is a circle. Spread in the point x0, y0, where actually x0, y0 are the real and the imaginary part of z0. So z0 in this case is x0 plus times y0. And the radius is r. Okay, do you hear me well now?
Right now, yes, but earlier when you were explaining the radius, it was dropping.
Oh, I'm so sorry. Okay,
Sometimes it
let's
works, other times it doesn't.
okay. Uh, I have tried some improvements with my connection at the internet while, but it seems that in this session, well, there is something that you don't understand. Okay, so this is a circle, and the domain which is bounded by the circle is called a disk. So the domain bounded by above circle 0 is less than r if we're talking about interior of the disk. And if you want to describe the disk and the circle, then you should put here less than or equal to, but we'll work only with this condition because we'll talk about the interior of this in all the cases, so we have to check this condition. Okay, how to make okay. So let's go with this 0, y 0. So this is the center of the circle, and let's say that this is the circle. This one in back is the curve which has this equation, and sorry, this space which is colored in yellow. This one is actually the disk, so it has the condition module of z minus z0 less than r. Okay, so this is the interior of the disk. This is it. Okay. Function S is analytical of delta, where delta is this domain. Okay, so I will denote by delta the disk, this disk. Then I equal to 0. Oh, and now I want to see some examples. Let's compute I, which is integral of this curve from the point from the function, sorry, 0 minus 15 squared sine 60. And second is, let's see. Let's see. How do you compute the first integral? So take a look at this expression. If this function well defined in all its points, so let's take a look at this function, which is sine of z over z minus 15 squared. Is this function well defined in all its points, in all the points of its domain? Is this function well defined on C, for example, on the set of the complex numbers?
It's not on 15.
Well defined on 15 because you're computing of 15, you have 0 here, and you're not allowed to have 0 here between the below the fraction line. So this function is not well defined in z equals 15. Okay, so f is not well defined in z equals 15. Let's represent points. You know that you have a complex number a plus r, where x and b are real numbers. Then to this point in plane, you have a corresponding point P of coordinates A and B. So in your case, z equals 15 is actually 15 plus 0 times I. So the corresponding point to this complex number will be the first, which is A, is 15, and then 0, okay, which is this one. So if I want to represent z in this plane, which is xy plane, I must represent 15 here. And the point corresponds to the 15. So f is well defined in all the points, but not here. Okay, you have to think at the plane, at this image, like a plane without a point, okay? A plane with a hole in it. It has a point which is missing. So, is this missing point in the interior of your domain? Let's see our domain. So, the contour of the integral is this equation. So you have of plus minus I equals 4. And I've told you at the beginning that this is the equation of a circle. But in order to find its center, you have to write expression between the module as z minus something. Okay, so first of all, I have to write again this expression, and this will be z minus 2 plus I equals 4. So take a look at this equation and at this equation, you will see that z0 is this value. Okay, so this is z0, and this is r. This is the radius. Okay, so 0 is minus 2 plus I. And it corresponds to the point minus 2 because I multiplied by 1 actually here. Okay, let me write again. This is minus 2 plus I times 1. Okay, so it corresponds to the point minus 2, 1, and minus 2 big point, let's say. So this is the third. So this is the third. center minus 2 and radius 4. So it is not such a big circle. Okay, it has radius 4, so it will look in this way, let's say. So this is the circle. And the domain bounded by this circle, that's delta, which is the domain bounded by the circle. We'll have the condition modulo of the plus r is therefore, because I'm the condition and I'm taking from less than is okay, so this is good. And that is domain actually. Okay, this is that. So is my function f well defined on delta?
Yes.
Yes, it is, because 15 doesn't belong to this domain. And a method for seeing that 15 is not in this domain is to draw the domain and to represent 15 in the plane. But another method is to use this condition to check if 15 is here. So if I don't want to make this picture, and if I want just to check this condition, I place here z by 15. So I will compute integral of, sorry, not integral, but the module of 15 plus 2 minus I. And this is module of 17 minus I. Let's recall that if we have to compute the module of A plus IB, then this is the square root of x squared plus b squared, where A and B are real numbers. So in this case, this will be equal to 17 squared plus 1, which is something more than 17, which is more than 4. So you don't have this condition fulfilled. So it means that 15 does belong to delta, okay? This is another method for checking if this point is in delta. And using both methods, we deduce that 15 is not here. So the function f is well defined on delta. And more than that, the function f is undefined. Okay, so it appears that f is well defined on also is undefined on delta, which means f is derivable on delta in each point of delta actually. So f is derivable on delta. And using this fact, and also using the Cauchy fundamental theorem, that the integral is zero. Okay. And since it was 0.15, my point with problems, my point is the yeah. Okay. Now I'd like you to try to solve the second point. To try to solve point B. which is this one. Okay, but tell me if you have questions until now. Do you have questions? I want you to 3 minutes to solve the point from here, and then we discuss. But in 3 minutes, try to solve it. I'm so sorry. I had a problem. I couldn't connect Teams. I had to restart my laptop, and now I'm very sorry. Let's continue. Okay, did you succeed to solve that point B? Can you hear me? Did you succeed to solve point
Yes. Is it
Oh.
analytical on the? Is it analytical on delta?
Yeah, it delta is. So let's write the equation of the contour. You have this equation, which is actually a circle centered in 0, 0, because you subtract nothing from z. So you have modulo of z minus z plus 0i equals 1. And
Use 1.
and radius 1. So it's that trigonometric circle that you know from high school. This is 1. And so your function fz is actually 1 over z squared plus 4. And this function is not well defined. When z squared plus 4 is 0. So when 1 is minus 2 and z is 2. So you have to represent those points in this domain, in this plane. Minus 2i corresponds to 0 minus 2, and this corresponds to 0, 2. Okay, so if you try to represent these points, then you'll see that you have 2i here and minus 2i here. Your domain delta is position where delta is much less than 1, and this position is not filled for Z1 and Z2. So that F is well defined. And also analytical. So using the theorem again here. Okay, do you right? So if you don't have questions, let's see other types of integrals, which will be computed using again Cauchy theorems. And let's see problem which helps you to compute the following integrals. So I will let you 1 minute to see what happens in this first case. So you could try to consider the function f to see where this function is not well defined, to represent domain delta, and to see if the point in which the function is not well defined is or not in the domain delta. Okay, I'll let you 2 minutes to try to find the points in which f is not well defined and to represent them. Have you found points in which f is not well defined?
The 2.
It's not bounded by the circle.
Yes. So it is not well defined on delta because 2 is in that is in the bounds.
Exactly. So f of z is cosine of z over z minus 2 squared, and it is not well defined in z equals 2, and the delta is given by z is less than 5. So if you want to check if 2 is instead of the picture, you have to compute modulo of 2, which is 2, which is less than 5. So 2 is in delta, okay? But if you want to see the picture, then this would be, you have and 2 is here. Okay, so this point and type. Okay, so in this case, you have two theorems that you can use. I'll write both of them, and then you will choose which one is appropriate in this case. So you have, sorry, you have this one, Cauchy integral, which says that if you have to compute I, which is a function which is computed modulo minus zero equals I, and you have a function f of z over z minus a z. So I be this integral. Let delta be the given by modulo of z minus z0 less than r, and a complex number which is in delta. Then I will be 2 pi I times of A. But I will write G of F to have this notation. So G of A. And also G is analytic on that. I equals 2 pi times G of A. Okay, so you know these facts, and you have that I is this one. I will write in this way, okay? And you have also Cauchy integral theorem, which says that if you have to compute I, but this time you have z minus a at the power n plus 1, delta again is a function, a is in delta, and it's a natural but g is big of delta, then you have that I is 2 pi I times 1 over n factorial times the derivative of order n of g computed in A. Oh, sorry, I didn't want to cut this part. Okay, so this are theorems which we use in this case. Which theorem do you have to use? Here's the theorems. Two different theorems. But this function, which form of the integral is more appropriate in this case? This one or this one?
Second one.
Yes, exactly, the second one. So n plus 1 in our case is 2, right? The point A is also 2, which is in this domain. So we have this condition fulfilled. And the function g is cosine of z, which is, of course, an analytic function on this domain delta. So two that we apply. Okay, so we're using theorem. And that plus 1 is 2. So it's 1. A also in the z is z, which also which sorry is an analytical function on delta. I'll write in this way, analytic. Okay, so using the theorem, I have that I is 2 pi times the g computed this point A, which is 2. So it is 2 pi times, if g is cosine, then g prime is minus sine of z, and this is minus sine of 2. Okay, and that's all. This is the value of I. So this is A. Okay, and now I'll let you again to take a look at point B, what happens with point B? So, case have here, or at least how many points you have the domain that or what the points in which F is not well defined? So let's this int denoted by the function f of z is 1 over z squared plus 1 plus 2, sorry, plus 2. Okay. F is not well defined. In which is minus root of 2 which is square root of 2i. Okay, so you have 2 points in which this function is not well defined. And let's see the domain. Delta is the domain bounded by this circle, which has this condition. Okay, now we have to take each of these points to see if they are in delta. So let's start with z1, which is minus square root of 2i. The I is minus square root of 2i plus I, which would be written as the module of I times minus square root of 2 plus 1. You know that if you have a complex number, then the module of z1 times z2 is the module of z1 times the module of z2. So this is what I'm applying here. And this will be equal to module of I times module of minus square root of 2 plus 1. But the module of I is 1, so this is the module of minus square root of 2 minus 1, which is square root of 2 minus 1, because this is positive. This was negative, so this could be So this is minus this expression. Okay, if it is less than 1, because square root of 1.4 and something, and minus 1 something less than 1. Okay, so we have Z1 is there. And if I'm taking a look at Z2, which is square root of 2i, I will see that the module of Z2 plus I is actually the module of this one plus I, which is the module of I times square root of 2 plus 1, which is again module of I times this expression. This would be 1, but this is positive, so this is square root of 2 plus 1. So it's greater than 1, and it means that Z2 doesn't belong to delta. So in this case, you have just a point which belongs to delta. This is Z1. And you have to write this function such that Z1 must appear here below the line fraction. So in this case, I have to write I in this way. If you have expression of degree 2, so it's expression of degree 2, then this is A times Z minus Z1 times Z minus 2, where Z1 and Z2 are the functions of the equation A squared plus Z plus equals 0. Okay, so you know that for the equation Z squared plus 2 equals 0, you have the solutions Z1 and Z2. So Z squared plus 2 is Z minus Z1 times Z minus Z2, which is Z plus I square root of 2 times Z minus I square root of 2. And this expression instead of this one, so I have Z plus this one times Z minus this one. Okay. And now to write only Z plus I square root of 2 here, which is Z minus this value. Okay, and this is 1 over Z minus this value. So C is A from the is minus A belongs to delta. We denote by G of Z this function. So G of Z, which is 1 over this expression, is analytic on delta because I of 2 doesn't belong to delta. Okay, so it's very important that this point, which is Z2, doesn't belong to delta because it gives you that G is an analytic function on delta. So you could apply one of the Cauchy theorems, and now I want you to tell me which of the theorems we will apply. The first one or the second one? So let's take this expression. Have in of U of Z over Z minus A. Okay, this is the good. So this expression is actually this one. So we are using the first theorem of this list. And we have that this I is 2 pi I times g of A times g applied to this point. So it is 2 pi I times g of A. And we are using the Cauchy integral theorem. And this is 2 pi I times, and g of A is actually g of minus I square root of 2. And then I have the root of 2 minus root of 2 minus 2 square root of 2. So I have here pi minus pi over square root of 2. Okay, so this is the value of I. Questions related to what we have discussed. Do you have questions? Okay. Then, if you don't have questions, let's discuss some advanced that we see at the students. Let's talk about isolate singularities of a function. You chapter to understand how to compute a residue of a function in a point, which is an essential notion for what you will study in the next weeks. So the isolated singularities of a function are actually points in which a function is not well defined. Okay, so these isolated singularities, as you have seen, of course, are divided into 3 points. And remove singularities and all for non-essential singularity and essential singularity. So if a function f, so let be a function defined B, which is a subset of C with value set C, and a point of C. We say that A is a removable singularity if the limit when Z approaches from f of Z is being finite. Then A is called a pole if the limit when Z approaches A of f of Z is infinity, And in complex, infinity is actually 1 over 0. So if you have something which is not 0 over something which is 0, you will obtain infinity. In complex, you don't have minus infinity and plus infinity. You have just infinity, and that's all. And A is an essential singularity. It's the approach A of Fc. Okay, let's do some examples. Let's see some examples. F of z is z squared minus 4 over z plus 2. Then F of z is z over c. F of z is over z squared minus 2z. And F of z is okay, so these are our examples. Let's see what type of singularities we have here. So a singular point is a point where the function f is not defined. Okay, so for example, for this function from here, the singular points are minus I square root of 2 and I square root of 2, because these are the points where the function is not well defined. For example, here, z equals 2 is a point where this function is not well defined. Also here, z equals 15 is a point where the function is not well defined. So they are all singular points, and in this example, I want to see which are the points in which these functions are not well defined, and I want you to tell me what type of points do you have here? Removable singularities, poles, or essential singularities? Because it's very important to make a difference between them. The seminar, we will work with poles. So the most of people will contain similarities. We won't talk about essential similarities because they're so much more complicated actually, because they need development of the function in Laurent series, so it is a little difficult here, but I want you to make the difference between these three cases. So let's take a look at this function, the first function. Can you tell me which are the singularities of this function?
A equals to minus 2 is a removable singularity.
Yes. Z plus 2 equals 0, so we have z equals minus 2, okay. And why did you tell me that it is a removable singularity? Because you
I'm sorry,
completely...
I was thinking of pole. I saw it goes to infinity. I don't know why I read for the removable
No,
one.
no, it's fine. It's a removable singularity.
Yes? Why? Doesn't it go to infinity?
Actually, because let's compute the limit as z goes to minus 2 from f of z. You will see that you have the case 0 over 0. So you have limit when z approaches minus 2 from z squared minus 4 over z plus 2. Okay, so this is limit when z goes to minus 2 from, and this z squared minus 4 will be 0 when you replace z by minus 2. So you have 4 times 4 here, actually. You have, just a second, I write with another color. You have 4, okay, minus 4, which is over minus plus 2, which is 0. Okay, so it's 0 over 0, and in this case, you get the limit just replace 0 minus 2. Actually, you have to make some changes here. You have to write this expression as a product. And in this case, you will see that this can be written as z minus 2 over z plus 2, everything over z plus 2. And then you simplify this one by this one, and simplifying them, you won't have a case, an accepted case, which is 0 over 0. So now you have only z minus 2, and if you replace z by a minus 2, you have minus 4, okay, which is something finite. So this here is something finite. So it means that this point minus 2 is actually because this thing complex. Okay, because z equals minus 2 is a singular. So your answer was correct.
By accident, but yes. Thank you.
Yeah, indeed. But it was correct. Okay, I will let you to see what happens at point B. What are your isolated points, and what type of singularity do you have at point B? Okay, I will let you 1 2 minutes to think about the following point. The isolated singularity is point. So when this function is defined,
Sorry, but we couldn't hear.
when this function f is not well defined, for what value of z this function f is not defined?
That's 0.
Exactly. For z equals 0, it is not well defined. So you have f of z, which is sine of z over z. So your isolated singularities are well, and then in order to see what type of singularity you have, you have to compute the limit with z approaches 0 from f of z. Okay, so this is the limit to z approaches 0 from sine of z over z. And it's equal
We do
from
L'Hopital.
there is no need to use the L'Hopital rule, but if you use it, it's fine, it's okay.
1.
Yes,
Ah, right. I forgot. I'm sorry.
sine of x over x goes to 1 when x goes to 0. This is the limit that from the high school. And in this case, this limit is available in the complex case. So you have that this is 1, which is also something finite. And in the end, you have that z equals 0 is a removable singularity. Okay, so it seems that you are again in the first case. And it's but let's go to point a squared minus 2z case f z of z squared minus 2z. What isolated singularities do you have here? And which are your isolated singularities?
0 and 2.
Exactly, because you have z squared minus 2z equals 0. So you have z times this one is 0. So z1 is 0, z2 is 2. Okay, two such ones, 2, 1. And let's start each of them. So the limit when z approaches 0, look at this one, from f of z will be equal to 1 over, and what happens if I replace here z by 0? I get,
Infinity.
okay, in the end I get infinity, so it means that z equals 0 is a pole of and limit of z approaches 2 from f of z will be 1
Zero.
over z, because 2 is a solution for equation so on equals 0. So equals 2 is a pole of f, and it's very, very, very important to know the order of the pole. The order of the pole is the algebraic multiplicity of 0. For how many times 0 is solution for this equation? For how many times 0 is solution of this equation?
One.
1. So the order of this pole is 1. It is a very important thing that you must know if you want to compute the residue of this function in the point 0. And the order of 2 will be the algebraic multiplicity of 2 for this equation, which is equal to
Also one.
Yeah, 2 so once. So also 1. And the point z. The point is 1 over z. So 2 is equal to 1 over z. And so
Zero.
yes, is not well defined, is 0. And let's compute the limit when z goes to 0 of f of z. It is e at 1 over 0, which is e at
Infinity.
infinity, which is,
Infinity. Ah, I'm sorry, we are in complex.
yes,
Yes.
it does exist in complex. Because if you're using the Euler's formula, you know that e at it is cosine of t plus I sine of t. But when you make t to go to infinity, then this will go to cosine of infinity. So we take t to go to infinity, and this will go to sine of infinity. But the problem is that cosine of infinity and infinity don't exist. So this will be if the yeah, it doesn't exist. Okay, so it means that z equals 0 is actually a point in this case is an essential singularity, but at the seminar we won't talk about them. I will have made just a problem with this type of point to understand that you may have such a case. So it is an essential singularity. Okay, and related with the isolated singularities, you have seen that you have the notion of residue. So we'll discuss a little about the residue of a function isolated singularity. Almost anything that will work at the same time will try this computation of a residue. Okay, so this is a very important notion. You must know how to compute a residue if you want to understand and to be able to solve exercises from the following chapters. So try to pay attention to what we are discussing and to what we see at the time. Okay, three types of singularities. We work with poles. You have a nice theorem which tells you that the residue of a function f of z in a point z equals a is 0 if a is a removable singularity. So I'm discussing the three cases. The residue function in z equals a will be minus 1 factorial times the when z approaches a from z minus a n times of z, and this expression must be computed derived by n minus 1 times. So this is the order of the derivative in this case, okay, of derivative. So you have to compute the derivative order n minus 1 in this case, where a is a pole of order n. We will work with n equals 1, 2, and 3, but you may have n greater than 3. We will work only with these three cases. And if a is an essential singularity, then this residue will be computed using the definition. Because the definition is not this one. The expressions that I have written above are actually theorems, are properties, which tells you how to compute a residue. In order to find the residue, if A is an essential singularity, you have to develop this function f in Laurent series, sent in 3 equals A. The singular series, so they also would have negative exponential. And you must find the coefficient of a term. So it is not simple to find a residue in general. So when you have essential singularities, you have to use a lot of calculus to find this residue, but we will work in the most cases with this formula because we will have poles of order n, and maybe sometimes you will have this case, but only in a small number of cases. Okay, so now let's look at the function. So let's have function f, which is 1 over squared times z plus 2. And to find the isolated singularities of this function to tell me what type of points are this one, and to find the residue of the function in the isolated singularities. Okay, so I want you to find these points and then we'll find the residue. I will let you 1 minute to think about the isolated and
The isolated singularities are 0 and -1, but 0 has multiplicity of 2.
X. So in this case, this function is not well defined when this expression is equal to 0, and you've told me that you have z1 equals 0 with the algebraic multiplicity equal to 2. Okay, that's perfect. And z2 equals -1 with the algebraic multiplicity z2.
1.
So what type of point are these? Let's find the when z approaches from F. This is 1 over 0, right? Because you are replacing z by 0, and 1 over 0 is infinity. So z equals 0 is a pole of order 2, because this is the algebraic multiplicity. Okay, so we have pole of order 2, and this goes to -1 for 3 is again already which is infinity, but z equals -1 is pole of order
1.
x. Okay, z and use this formula for n equals 2 because n is order, and then for n equals 1. Okay, so let's see. Let's find the residue of a function of the function f of z when z equals 0. So this is the point of order 2, so it means that n is 2. And let's take a look here. 2 minus 1 factorial times the limit when z goes to this point. Okay, z goes to this point. From z minus this point, which is z minus 0, the n, which is 2. Okay, this n is 2, times the function. I will just copy this function, which is 1 over z squared times z plus 2. Okay, and this will be computed. The derivative will be computed once because you have derivative order n minus 1. In your case, n is 2, so you have the derivative of order 1 of this function. So it's this one. Okay, so this is equal to 1 over 1 factorial, which is 1, times limit when z goes to 0 from z squared times 1 over squared times plus. Okay. And what to do? Well, in this case.
Sorry, did you
So
ask
you
about the derivative?
the
Interrupted.
expression.
We simplify the squared, and then we do the derivative of 1 over z plus 2, which is -1 over z plus 2 at second power.
Yes. And the residual
Isn't it -1 over 4?
of, sorry, 2 squared. Sorry. This is the residue So you will see that this number of residue will help you a lot to compute complicated complex integrals and also compute real integrals that you know from the high school in a very, very easy manner. So you will see in the following seminars. And now let's find the residue of the function f of z in z equals -1. Okay, this is over. This -1 is the or the 1, so it's 1. Again, we are using this formula. So we have 1 minus 1 factorial, which is factorial times limit when z goes to this point, -1, from, and we have z minus -1, actually. We have z minus -1, which is z plus 1, of the power n, which is 1, times the function z, which we call, sorry, I have written another function here. Is my mistake. This is 1. I have changed the function from one page to another. Okay, in my mind it was a 2, but actually it is 1. Okay, because I have written here 1. 1 and 1. Sorry again. And this is 1. Okay, so this is from X minus. I've realized now. Step to compute the derivative of this function. N is 1 in your case.
We don't.
Yes, don't, because you have here 1 minus 1, which is 0. So you have the derivative for the 0. So you have the function without computing the derivative. This is the expression. This is 1. And you have here a very nice simplification. You have the limit when z goes to -1 from 1 over z squared, which is 1 over 1. So residue of function z equals -1. Have you seen this theory?
No.
Okay, not yet, but on Thursday we'll discuss things at the seminar, but we'll discuss them with more details. I wanted to point this theory today because I wanted to give you some extra explanations about these points. We started with computing integrals. I would like to finish by computing all integrals, but not by using the Cauchy's theorem, using actually the residue theorem. So the residue theorem tells you that if you have to compute I, and let's take circle, and it's a function f of z t. So if you compute this I will be 2 pi I times the sum of the residues of f computed in all the singular which are delta, where delta is domain bounded by circle. So delta is the disk. Okay, so you want to the integral, and function f is complicated and it has a lot of points, a lot of singular points in the interior of this disk. Then first I have to find the singularities of f. So the first step, find the singularities of f. Then choose the singularities which are in delta. Compute the residue of f in those singularities with delta. And up to I times sum of two. So these are the steps. And for example, say that you have to compute I from this function of this circle. I will let you 2-3 minutes to decide if you can use one of the Cauchy theorems to solve this problem, because at the beginning of this session we have discussed about the Cauchy theorems, and you have seen that there are 3 theorems. This is the fundamental theorem, this one, which tells you that if f is well defined in this domain and it is analytical, then I is equal to 0. Then we have discussed about Cauchy integral theorem and Cauchy integral theorem for derivatives. And, please tell me if you could use one of them to solve this integral. I want you 3 minutes to think of this fact. Apply Cauchy theorems for this integral. So see the isolated singularities of function f. Okay, so let's say that f is the isolated singularities of f. We have seen before that there are z1 equals 0 and z2 equals -1. Okay, so you have z1 equals 0 and z2 equals -1. You use the Cauchy theorem for more than 1 point in that domain. So in the Cauchy theorems, you had just a point in which this function was not defined. Just a point which was in the interior of the domain delta. Let's see if these points are in the interior of delta. So we have delta, in this case, is the domain bounded by this circle. So this is the condition of delta. And let's see what happens for z1 equals 0. You have that the modulo of z1 is actually modulo of 0, which is 0, which is less than 2. So it means that z1 is in delta. And so z2, which is minus 1, is in delta because it's modulo which is less than 2. Okay, so delta is actually the disk centered in 0 with radius 2, and minus 1 is here, and 0 is here. So z1 and z2 are actually in the, okay, have 2 points in that. So the theorems were used when you have only 1 point in that, 1 point, not 2 points. So having 2 points in delta is something complicated because I must write this function as a sum of 2 functions, each one having just a point in delta. But this is a particular case in which I could do this fact. But if I have hyperbolic cosine instead of 1, this is much more complicated. So the idea is to try to use another result to compute this integral because the Cauchy theorems won't help me here. So I use the residue theorem, which helps me to solve this if I have more points in this domain. Okay, but first I have to find singularities of F, and I found them. There are Z1 and Z2, so there is singularities. Then I have to choose the singularities, the points which are in delta, but I have checked and both of them are in delta, so I have to choose both of them. Then to find the residue of the function f in each point from here, but I will use the results obtained earlier, and I already have the residue computed in each point. So I have residue of z equals 0 minus 1, and I know that residue of f in z equals minus 1 because I've computed them earlier. Okay, and I have this step accomplished. So in the end, I have that the integral I from here will be, according to this theorem, 2 pi I, so it's 2 pi I times the sum of the residues of the points which are in delta. So residue of f of z in z equals 0 plus residue of f of z in z equals minus 1, which is 2 pi I times minus 1 plus 1, which is 0. Here's I 0. But because we apply the fundamental Cauchy theorem, because it cannot be applied here, but because we apply this residue theorem. So do you see this theorem helps you to find the value of each integral? It doesn't matter how many points are in delta. And to see if you understood what we talked about, I would like you to take an integral from here. Okay, so let's say this one. was computed using the Cauchy integral theorem for derivatives. So we computed it using Cauchy theorem, and now I want you to compute it using residue theorem. Okay, so I will copy this integral here, and this would be the last example for today. So I want you to find the value of this theorem. Use the theorem, which is please to find the singularities of the function, then to choose the points which are in the interior of delta, and to find the and then to compute the integral using this formula. Okay, I'll let you 2-3 minutes to think about the solution, and then we will discuss. Have you tried to think of the solution of this problem?
Is the singularity removable?
So if we know this function of fc, the isolated singularities of actually are 2 points which are the same, z equals 2, and in order to find the type of point is this one, we have to compute the limit when z goes to 2 from f of z. Okay, so this is limit when z goes to 2 from cosine of z over z minus 2 squared. What happens when you replace z by 2?
We get infinity.
Yeah, it goes to 0, so it so it is that z equals to all of 1. And the algebraic multiplicity. The algebraic multiplicity of 2 in this case is
2.
So because when you solve the equation, this expression equals 0, you have twice the solution 2. So because this one is 2, the order will be 2. Okay, and now you have to see if this pole is inside this domain. So delta is this, which is this condition. And compute more 2, this 2 is less than 4. So that you have to compute the value of in this point, which is 1 over 1 times limit when z goes to 2 from. And let's take a look again at this formula. N is 2, so this is 1 over 2 minus 1, which is 1 over 1, which is 1. We didn't write this fraction, times limit when z goes to 2, from z minus the pole, the order of the pole. So you have here z minus the pole, the order of the pole, times f of z, which is cosine of z over z minus 2. This expression works because n is n minus 1 here. So it's and this is 2 goes to 2 long, and the cosine is sine z, which is minus sine of 2. Okay, so this residue is minus sine of 2, and when you apply the residue here, 2 pi I, okay, from the theorem, from here, it is 2 pi I times the sum of the residues, but I don't have a sum. So this will be minus sine of 2. And if you take this expression, you will see that it is exactly the same with the one that you have computed here. Because actually, this 2 pi I comes from the residue theorem. This 1 over 1 factorial is also from the formula of the residue. And this g prime of z is the derivative of the cosine computed in the pole. So it is minus sine of 2, actually. Okay, so this theorem, this Cauchy theorem, is just a particular case. Each of them are particular cases of the residue theorem. Okay, so both of them could be replaced easily by this theorem, which is called the residue theorem. It is much stronger than Cauchy theorem. And you will have the same result. Then you have questions.
I have one, but it might be a bit stupid. But could we split the integrals, like for the previous example when we had 1 over z squared times z plus 1? Would we be allowed to split it into 1 over z cubed plus 1 over z and compute each of them with Cauchy?
Made you could split it into parts. If you have this expression, you could split it. You could find a and b such this is a over z plus b over z squared plus z over plus c over z plus 1. And then the integral of this one will be integral from each one. So no point the Cauchy theorem cannot apply when you have a complicated expression here. For example, if you have a sine of z over z squared times z plus 1 times e at 1 over z. Okay. When you have this expression, it's much more difficult to write this integral as a sum of integrals as we did here. So this is why the residue theorem is more useful in this case. Your remark is very, very good. So you could write this integral as a sum, but with some time, because you have to find the coefficient a, b, and c, and then apply Cauchy theorem for each of these integral. And if you're having here a much more complicated expression, that will take you much more time to find these constants a, b, c. So Cauchy theorems help you here, but it will take you some time to apply them. Instead, the residue theorem is faster than writing this integral as a sum and applying for each one the Cauchy theorem.
Okay, thank you.
That you some problems that when you have essential singularities, you cannot apply Cauchy So when you have singularities and you apply theorems. But when you are in this case, Cauchy theorem won't help you, none of them. So it is mandatory to use the residue theorem. They could be computed only using the residue theorem when you have essential singularities. For example, an integral of this function. Okay, so that's why this residue theorem is so important. If other questions?
I have a question, but it's outside of this lesson. When are we supposed to get the results for the partial exam?
I sent the result to somebody yesterday at 9 o'clock in the evening. He wrote to me today that he has received the email, but I guess that it will take some time to make the sum of the marks that you have at the theory part and the problem part to make a mean and to post the final results. So next days, maybe, I think that this week for sure you will have results because you already the result. But this week I hope that you will know what you did in your partial exam.
Okay, thank you. And sorry for
You're
asking.
welcome. You're welcome. Do you have other questions? Okay, if not, please again this to see who is here. Just and was connection better than last time? I know that it was interrupting sometimes, but was it better than the last time?
It was still interrupting today too, unfortunately.
So it's the same thing. You
Yeah,
cannot
I
see a
would
difference.
say it's pretty much the same.
Oh, I'm so sorry. I'm so sorry.
It's okay,
It's okay.
mainly because we are also seeing what's written on the board. So whatever gaps there might be in the sound, we can see it written.
Yes, exactly. You have the word, but I'm still sorry. John, Pop, Sam, are you here? Can you hear me?
Yes,
Yeah.
now yes.
Oh, speak. You are because I have talked to you earlier. Oh, Blue, Alexandra. Okay, Nika. Or
Da.
Toma. Okay. Ada Scăliței.
Yes.
Roman, Gulida.
Yeah.
Jacques,
That
Tudor.
here.
No. Alina.
Aici.
Okay. Andra, I've talked to you a lot. Badică.
Aici.
Okay. Prodan. Oh, it appears that he left. Okay. Your school and Nika. Thank you very much. If you have questions, so we could discuss this week or other time.
I see that someone has written in the chat.
Yes,
should look.
yes. Anna replied. Okay, they have told me that they are here with us.
Teacher, I also wanted to apologize for me and some of my colleagues. I forgot that we had this thing weekly, so I entered later, and some
Oh,
others
it's
didn't
fine.
know. But
It's fine.
from next week on, we will know. I'm sorry. I thought it was only for the partial. I understood wrong.
No, stay calm. It's a project. Will take place in every week.
Okay, thank you.
So welcome. Okay, I've seen that you have written in the chat. Okay, that's perfect. Thank you. Have a nice evening and have a nice week too. See you on Thursday at the Goodbye.
Goodbye.
Thank you. Have a nice evening.
Goodbye.
Thank you.